Please go ahead.
Hello, everyone. My name is Ali, and today I will be presenting my ongoing research um, towards evolving creative algorithms, musical time series forecasting with Tangles program graphs with Stephen Kelly, my supervisor. So, what I've gone from this conference so far is that everyone has a separate definition for a word, but the way I like to describe creativity is from the Cambridge Dictionary. It's the ability to produce or use original and unusual ideas. So combining this with AI, we're basically trying to mimic humans' ability to produce or use original and unusual ideas. And the way we're doing it is with the generation of music, which is a good way to show creativity. So the goal of this research is basically taking one song and capturing its patterns, using those patterns to produce more music. In this way, we're essentially creating an algorithm that has the ability to capture what humans have created. But there are a few challenges in musical generation. The first one being that the representation of music is a little obscure. So how can we take a MIDI file, which is the standard for music, and converting it into something that can be converted back to MIDI without that much loss of data? Furthermore, songs are non-stationary, so the time is always changing. It's hard to normalize it, right? And the takeaway is kind of to use time series. However, this leads to the next drawback. This leads to the next challenge. Yeah, so I'll just continue. It leads to the next challenge, which is the drawbacks of modern techniques. So if we use statistical methods, the data must follow statistical assumptions, which is hard for music, and it's very window dependent. So it has trouble focusing on long range dependencies since it's only looking at a stagnant window. For neural networks, they're complex. One network would easily have over 100,000 usually, and the complexity changes based on the window size changing. So if you use a larger window size, the complexity, like the neurons, would probably be more. And finally, the final challenge is the lack of data. So if we were to use one song, the song would usually only hold 500 to maybe 2,000 time steps, depending on the genre. And capturing these sequences is hard, but generating music is even harder. So for these challenges, we propose the following solutions. For the representation of music, we use sequential time series data. And for the drawbacks of modern techniques and the lack of data, we utilize something called Tangled program graphs. So for the representation, it's represented as a multivariate time series where we have the offset, which is the location of the note in seconds, the duration, which is how long it's held for, and the pitch, which is a value between 1 to 127. That's derived from the MIDI file. That's the standard. And this is a regression task. So um, we predict the next pitch based on the current one, and it's evaluated on its recursive forecasting ability with the window size of 50. So here we can see a window size of 4, and it's predicting the next value. So after it predicts that value becomes its input. So it goes into the window, popping the least recent value. And this goes on until eventually you'll have a window of just your predictions. So what are Tangled program graphs? Tangled program graphs are a genetic programming framework designed for reinforcement learning. The way it works is that you have your initial population, and it's a hierarchical structure where the top is represented by teams of programs. And this team of programs, the programs either point to an action, which is a continuous value for our sake, and or they point to a team, and that usually comes through evolution. So at the end, something like a tangled program graph emerges where you can have a team that consists of a program which can point to another team, or it can point to a continuous value. So then the question arises, how are these programs chosen? These programs are basically linear genetic programs where it consists of registers and instructions. And the input, so in our sake, it's the window size of 50 values is given in, and two values are produced or given to us, which is the prediction, the value we're predicting. So in our sake, it would be the next time step, and a bid value. And this bid value is used to make the decision which program to choose. So the higher the bid, the more likely it is to be chosen. The benefits of TPG over, say, neural networks are that the complexity is fairly low, where you have operations of around 1,000, and neural networks have easily over 100,000. And if you're talking about deep learning, over 1 million. And the cool thing is that since it captures the behavior, the operations are updated at the end of the generation. So it's less likely to overfit, meaning you can have overlapping training, testing, and validation, since you're capturing the behavior rather than updating the operations after every time it looks at a number. So for our experimental setup, I used Ava Maria by Bach and Gorand, and this is how the first episode looks, where the starting point for the training procedure is random, and it's primed for 50 time steps. So this priming is essentially you're warming up its internal memory, and then it forecasts for the next 50. So this 50 is where the error is accumulated. For validation and testing procedure, we primed it sequentially rather than random for 50, and it's forecasted for 100 rather than 50. And the three fitness functions, you're probably all familiar with mean squared error, where you just take the difference between the target and the prediction and you square it. We looked at Pearson correlation, which looks at the linear correlation between two data sets, and we looked at U of Thiel, which is basically MSE, but you divide it, you normalize it by a random block forecasted error. So the results, um, we ran 20 runs per fitness function. So these are the 20 runs for U of Thiel's, MSE, and Pearson correlation. And since these are different metrics, we looked at one common metric, which would be MSE in this case. And Pearson correlation obviously performed the worst because it's just the linear correlation between the prediction and the actual value. The MSC was the best overall. So off of 20 runs, you would have the best average. You have the best average. And U of Thiel's had the best overall agent. So when we look closer at the agents themselves, you can see Pearson correlation did not do well. MSC was kind of getting it, and U of Thiel did pretty well. The nice thing about it also is that even though it was trained for 50, the horizon was 50, it continuously still captured the rest for a horizon of 100. So as a conclusion and future work, we basically propose using Tangled program graphs for recursive time series prediction in a difficult task music with limited data, and we utilize different fitness metrics. U of Thiel's produced the best agent, which makes sense because it's double the iterations. MSC had the best overall, which you would use for if you want faster convergence. And for the future work, we want to consider multivariate prediction and try more representations like one-shot encoder. I avoided using one-shot encoder just because of the loss of data. Thank you, but wait, I decided to keep this just in case I have extra time. I am assuming you guys are all curious how the music sounds. So the first 11 seconds are the actual song, so don't be impressed by that. The rest, you'll realize when it turns bad. This is where it turns bad. Longer. Okay, yeah, I guess you guys get the point. But yeah, so that was past the horizon of 50, what it was trained on, and that was even I think more than 100. So that was pretty cool, I think. Thank you.